First, I would like to thank the QHack community for giving me the opportunity to share some of our work with you guys and with everyone in chat. I think QHack is one of the greatest events online. The community that forms around it is amazing, so I'm really happy to be here again to share some of our work. So today I'm going to be talking about this thing that we call geometric quantum machine learning, and I'm going to be presenting some of our results as you see here. And I think that with this community, it's really not necessary to explain what quantum machine learning is or why it is important, but I'm going to try to just very briefly go through this. So we already know that machine learning is one of the most disruptive technologies that we've had in the past few years. It allows us to learn and classify data and find patterns, and it's just essentially revolutionized all areas of technology and scientific research. And we all know that the main idea of quantum machine learning is to take the learning formulas of machine learning, trying to combine it with quantum mechanics, and try to see if we can do anything that we couldn't do otherwise, right? And of course, the hope is that by harnessing the power of quantum computers, we can outperform classical devices on learning tasks. This is where the quantum machine learning part comes in. And for me, this is going to be important for quantum data, but also we can talk about classical data. So first, let me just set the stage. We're going to be talking about supervised quantum machine learning in this case, so that machine learning is very broad. There's a wide variety of things that we can do. But for today, let's just focus about a supervised search. So what do I mean about that? So we're going to have a given data set, which I'm going to call D, which is going to be composed of quantum states. There are quantum states on n qubits, and there are associated labels yi. And the whole point is that we assume that there is some underlying function that takes a state and it assigns a label. This is the function f, right? And what we want to try to do is train a quantum machine learning model, which I'm going to call H, and it's parameterized through some set of parameters in some way. And we want to try to reproduce the labels in this data set, right? And we want to do this for the training data, but also for new and previously unseen cases. And whenever I talk about a quantum machine learning model, there's a lot of things that come into play here. This is a very abstract thing, but as we will see, we're going to talk about quantum models that are parameterized through quantum neural networks, where we choose some form of measurements in a quantum computer and some sort of post-processing that we're going to do to it. And it's been shown that the success of a quantum machine learning model greatly, and in general of machine learning models, not just quantum, but also classical, they depend on what are the inductive biases that go into this model. So what do I mean by an inductive bias? Well, it's just the assumptions or the information that you put into your model. I'm going to use this set of gates in my quantum computer, right? I'm going to arrange them in this way. I'm going to measure this operator. These are all choices that you're making that might be arbitrary, more or less, and those are going to define what your model is. And what's very interesting is that there's been a lot of work trying to show that if you have a quantum machine learning model that doesn't have any inductive bias, that means that it's very general, then it might have poor performance. It might have barren plateaus. It might have poor generalization. So the whole point is that these inductive biases, or what are the choices that go into your model, are extremely important, right? And what we're going to try to do is find ways to create good inductive biases by analyzing our data. So let me just give you here, let's think about classical machine learning, a supervised machine learning problem of classifying cats and dogs. And I'm going to give you an extremely crazy claim, which is that if I give you a picture of a cat, now I take the picture and I take the cat and I just move it, so I translate it and I rotate it, well, this is still a cat. This is my crazy claim, right? And what does it mean to translate and rotate? You just move the pixels in your image. So as we can see, we can always take a picture of a cat and it's still going to depict the cat if we roto translate it over the pixel group, right? So what does this mean? And the cat, the image in itself is not changing, right? It's a completely different picture. However, the label of the cat is invariant under the roto translation group, right? So this just shows us that data has symmetries associated to it, right? And spoiler alert, quantum data also has symmetries. Say that I give you the problem of classifying states that have those are spins, and they have ferromagnetic type alignment, where the qubits are going to be aligned in a parallel fashion, or they can be aligned in an anti-parallel fashion. Well, you can see that if I have two qubits that are parallel and I rotate them by the same rotation, they're still going to be parallel, right? So we can start to see this idea that data has symmetries, right? And the question that we're trying to answer is, how can we use that symmetry information to try to create better learning models? So one thing that you can do is that you can try to have your model learn this invariance via what is called data augmentation, which is just, okay, there's a picture of a cat, I give it to my model, it gives an accurate prediction. Then I give it a rotated picture of a cat, it might be confused, it might have to learn that this is also a cat, and I might have to give it a bunch of pictures of cats rotated in different ways. But the problem is that now the model might just be saturated, it might just be it might not have enough capacity because we're just giving it so many pictures of the same cat that it's just roto-translated. So how do we solve this? We just make our model larger. We just put more parameters in it so that it can learn this invariance. And we can just continue doing this a bunch of times until eventually, we just fed it enough pictures of the same cat that is roto-translated, and now it might just have learned this invariance. But the problem is that, as you can see, this is very data and parameter inefficient. And what's even worse is that whenever we get a new picture of a cat, we just present our model with a new picture, it might just have overfits. So we don't have a guarantee that the invariance that it learns over the data set might be generalized beyond what it's learned, right? So what is the solution? So we want to try to do is that we want to have models that are invariant by design, so that somehow we've baked all the information of the symmetries into the model so that it doesn't have to learn it. If I feed it a roto-translated cat, it just sees it as the cat, Now, the problem is that this all sounds too good, I'm being very abstract. This almost sounds even too simple, right? But the question is, how do I go about baking those invariances into my model? If you're working in classical machine learning over the past, I would say like 6 or 7 years, there's been a lot of really smart people that have been working on how to understand symmetries in classical machine learning model. And this has sort of coalesced into this field that people nowadays call geometric deep learning, which, I really recommend this article right here. You can find the archive identifier here. It's not an article, it's a book, and it's a beautiful book. And they show that the most successful machine learning models the most successful classical machine learning models are the ones that naturally respect symmetries. And then they're trying to extend this to how to create new models that will encode symmetries. And I will also recommend this link right here. It has a bunch of papers that have been compiled for bibliography on geometric deep learning. And the core ideas of geometric deep learning is they've recognized the importance of symmetries. And we were just talking about the roto-translation group, but this can be generalized to other groups. And it has already been applied to many domains like analyzing spherical images, graphs, molecules, because all of those contain symmetries, right? So now let's take a step backwards. What are we actually doing whenever we put symmetries into our model? So you can think about, this is the function space, all possible functions that map from data to labels. And we're just trying to find one function is in here. So if we have a model that doesn't have any prior information about the geometry in the data and the symmetries, its search space may be very, very large, right? And we might be trying to find that model out there. But whenever we embed symmetries, we might just restrict its search space to in a problem-inspired way to just try to simplify our task, right? And you can think about the fact that whenever you have generic models, you will have no free lunch theorems, where we know that generic models that you can use for any task, so going back to quantum, if I use the same circuit, it's just a hardware efficient ansatz where I do rotations and CNOT chains, and I do this for BQE, for generating models or whatever, it cannot have a good performance because the no free lunch theorem tells you that multi-purpose models that you can use in a wide variety of tasks are going to have a poor average performance. Whereas if you take a model and you specialize it for a given task, it might have a very good performance. So this is what we're trying to do in geometric quantum machine learning, which is just taking the ideas of geometric deep learning and importing them to quantum machine learning and finding ways in which we can create models that encode the symmetries of the problem at hand. Because the thing is that some of the tools that people use in classical machine learning aren't really that directly transferable to quantum machine learning. So we really need to analyze how the same ideas can be applied with the quantum formalism. Now, I'm going to make a disclaimer here that despite the simple ideas of geometric quantum machine learning, whenever you want to try to go and implement it, you need to have some significant amount of knowledge of group theory and representation theory. So we already know that group encode in an abstract way symmetries, right? And they compose as a group. So a given rotation, I have a rotation and another rotation, I compose them, that's a rotation, right? So the composition rule of a group, you can see that it applies to symmetries, right? And representation describes how an abstract group acts on a given vector space. So for instance, let's go back to this idea of rotating vectors, right? So now the abstract group is just SO3, and this is just completely abstract. Now I need to say, all right, let me think about a 3 times 3 vector, and how is this rotation group going to act on this 3 times 3 vector? The vector defines a vector space. Well, representation theory maps from the abstract group to 3 times 3 rotation matrix, right? And for people that want to learn more about representation theory, we've written this sort of like tutorial. This is by quantum machine learning practitioners for quantum machine learning practitioners. So we're trying to give an idea of what are the basic tools that people need for representation theory, how to use them, and this is completely example driven. So this is going to have a bunch of examples in it to show people why this is important for quantum machine learning. So in what follows, I'm going to try to be more explicit and show how to use this, right? So first, we need to agree on some setting. For us, my model is going to be, I take my data, I send it through a parameterized circuit, or what I'm going to call a quantum neural network, and I'm going to make some measurement of an operator O at the end. So that my model, the action of the unitary, can just be expressed as a channel where I just conjugate rho via some unitary. And my model looks like this, where here I've used the trick that because the channel is unitary, you can think about the Heisenberg picture, where instead of making your state evolve, you made your measurement operator evolve, right? So this is the setting that we're going to be working. And the main question is, just with this, how do we build a model that respects symmetries? So the first thing that we're going to do is consider that we have some symmetry group G and a model that looks like this. And the claim is that you can make the model invariant under the action of the group if and only if your measurement operator commutes with the action of the group. That means that it belongs to the commutant. I know I'm going to try to not do a lot of math. I'm sorry about this, but the commutant is just the set of all D times D matrices that commute with all the elements in the group. So you want your measurement operator to belong to this set. And you can see it very clearly here. I take an element of my group, I make it act on rho. I'm just going to assume that it just acts like a rotation on my quantum state, and then I'm just going to use cyclical property of the trace. I can put the R to the right here. And then I've already said, but the operator O commutes with R because it belongs to the commutant. So I can just pass it through. Now, these are just unitaries. They cancel each other. And you can see that now the output of my model is exactly the same for the state rho and for the rotated state rho. So now I have a guarantee that by design, my model already produces the same result despite me feeding it a state or a rotated state. And this is just like the cat. Whenever I take a state and I rotate it, my state changes, right? So again, very abstract. Let's go to something even more concrete. Consider the problem of classifying single qubit states according to their purity. So we can visualize this. So we can put all the pure states on the sphere, on the block sphere, this is going to be in the outer shell. I'm going to assign label 0, and then I'm going to assign label 1 to mixed states with a given purity. And I want to classify them, right? The first thing that I need to do is I need to identify the symmetry. Here it's very simple. The symmetry group is just the unitaries. I take a state, I apply a unitary, I get a completely different state, but the purity of this is the same as the purity of the initial state. So this is my symmetry group. Now I need to find a suitable operator in the commutant of G. And what this is going to look like, again, it depends on who H is, right? So for instance, let's think about a model where I'm only allowed to act on one copy of rho. Well, in this case, you can check and you can use representation theory to say, and I'm going to say something, don't worry if this doesn't make too much sense. This representation of the unitary group is irreducible, and hence the commutant only contains the identity. In other words, you can try to find what are the matrices which commute with all the 2 times 2 unitaries, and you will find that only the identity does this. Now I need to pick this operator in here, but there's nothing that I can do, because if I take my measurement operator and I just replace an identity, I get trace of rho, which is 1 for pure or mixed states. So that means that if I only use one copy and I find U invariant models, I cannot classify states. But now let's consider a model where I'm allowed to feed 2 copies of my quantum state. And now I want to see who this measurement operator is. So now you can see that whenever I want to rotate my states, the action of the group is now U tensor U, because I need to rotate the first qubit and I need to rotate the second copy of my qubit. So now we can ask the questions, what are the matrices that commute with U tensor U? Not very hard to see that you have the identity times identity. This always commutes with whatever, and swap. If I have U on the first qubit, U on the second qubit, and I swap them, it's still U tensor U. So now I can measure an operator O that belongs in here. And what happens if I actually pick swap? Well, we already know that if you pick swap, the trace of swap with rho tensor 2 is just the trace of rho squared. And that's actually the purity. So we found a non-trivial classifier just from purely considering symmetry conditions, right? But now the problem here is that we were able to just directly inspect identity, and swap and say, oh, if we pick swap, then we get the trace of rho squared, and this solves the purity classification problem. What happens if this commutant is very big? We can't just really inspect every one of those, or characterizing the commutant might be very hard in itself, right? So the idea is that we want to find a systematic way to characterize and explore this commutant. And in particular, we're going to do this in a way in which we're going to parameterize the commutant and we're going to explore it. And this is where the concept of equivariance instead of invariance comes into play. So what we want to do is design and parameterize group invariant models. So let's go back to this approach where we take a unitary and we apply it to O. And let me just assume that this unitary just contains multiple layers, and each one of those layers is just e to the minus I theta h, right? It's just take a Hermitian operator, exponentiate it, and rotate your state, and you do this multiple layers at a time. So how do we define equivariance? We're going to define an equivariance layer as a map that commutes with the action of the group. Again, this is just the same. If I take a state and I rotate it at the input, this just commutes through, and it's the same as applying the unitary to my state and then applying the rotation. And it's not very hard to see that if I have equivariant circuits and equivariant measurements, the whole thing is going to be invariant, right? So now the problem gets translated into how do we build this unitary channel such that it commutes with the action of the group. I'm not going to go into technical details. I'm just going to say that we've built a toolbox for constructing equivariant quantum neural network, where the idea is that you have data, you identify a group, you identify its representation, and we provide how to build those equivariant layers. We've provided 3 different alternatives. Again, I'm not going to go into all of those details now. We've analyzed their scaling, how hard it's to actually do this. We've provided examples for different special groups, and we've also been able to characterize different types of equivariant quantum neural networks, like embedding, where you take classical data and you put it into a quantum state, and you can make this process equivariant, or standard layers like a unitary, but also like pooling and projections, where I'm throwing qubits away, right? And the goal of this paper right here was to understand the action of equivariant quantum neural networks. What are they actually doing? Again, this is after every slide that I give that is very abstract, I want to try to ground this with an example. So again, we already did purity. Now let's do a classical data example. Imagine that your data is just 2-dimensional vector, real values, and it lives in a plane like this. And I'm just going to say the data that lives in the green region has label 0. The data that lives in the yellow region has label 1. And we can see that there is a symmetry. If I just swap x by minus x, the label gets preserved, right? So now, again, what is my group is just going to be Z2. This is the abstract thing. Z2 has 2 elements, identity and another element. And whenever I square this element, I get identity. Like, I can do nothing, I can reflect, and if I reflect again, I go back to the initial state, right? So this is why I can identify my abstract group as Z2. What is the representation acting on this plane? When is just change x1, x2 to x2, x1. This is, we can see abstract group and its representation. Now I want to solve this classification task on a quantum computer. I need to take classical data and map it into quantum states. All right, I'm just going to do angle encoding, right? I'm just going to take rotation around the x-axis and rotation around the x-axis. And here I have to give full credit that I'm partially taking this example that was explored in this amazing paper by Johannes Meyer and the ISER group. Really beautiful paper, go and read it. And we can see that what I'm going to be doing is taking the first component of my data vector, rotating a qubit, taking the second component, rotating a qubit. Now, do we still have symmetries after this rotation? Well, we actually do. We can see that if we swap the qubits, it's the same as doing this. So now the same group is living in a different, is acting on a different vector space, and we have to find a new representation given by identity swap. So we assume a model where I'm going to send this data by a parameterized quantum circuit. How do I go about finding equivariant layers? Well, the claim is that if the generator of each layer is in itself in the commutant, then your layer is going to commute. You can prove this. The proof is also in this paper by Johannes. So now we've translated from finding unitaries to finding generators of the unitaries that belong to the commutant. And we've already said characterizing the commutant might be hard. How can we get such Hermitian operator? Well, you can do this thing that is called twirling. If I give you a group G, you just take an operator A and you apply the action of every element in your group, and you just apply it to the left and to the right dagger, and you make a summation, right? And what's pretty cool is that this operator, once I just twirl it over the group, it belongs to the commutant. Again, abstract, let's go to something concrete. Say that I want to implement X1 as a gate in my quantum computer. Well, I need to twirl it. That means apply identity, X1 identity, plus swap X1 swap. You can see that this gives me X1, X2 divided by 2. So this is great. Now I have this, and I know that if I exponentiate this operator, it's going to be an equivariant layer. What happens if I want to do an entangling gate like Z1, Z2? Well, we do the same thing. We apply identity and we apply swap, and we get the same thing. Oh, this was already equivariant for this representation of the symmetry. I didn't have to do anything. So now I can just create a circuit that is going to evaluate the data, which is going to be e to the minus I theta ZZ, YY. And again, remember, when I exponentiate this means do single qubit rotations with the same angle theta 3. And now what's really cool about the circuit is that if I apply a symmetry operation in the classical data, it's going to translate into a symmetry operation here, which I can commute all the way through to the end of the circuit. So this whole pipeline respects the symmetries of the classical data. And this is very important because a lot of times whenever we take classical data and we put it in a quantum computer, all the symmetry information is just completely gone whenever we do our encoding. Now, we're losing information here. Maybe we can still do something. But if we create good embedding models and good quantum neural networks that respect the symmetries all throughout the pipeline, we know that this should perform better because my model is going to be restrained to the section where it's going to explore the functions that respects the symmetry of the data, right? So coming up with good embedding schemes for me is something crucial for people that want to work with classical data. If you take classical data and you put it in a quantum computer, ask yourself, what happened with all the symmetries? If they're all completely gone and lost, then there's probably something that can be done. So let's go to some more concrete examples and show the power of geometric quantum machine learning. Let me just consider the problem where I have my symmetry group is going to be the symmetric group, which is just the group of n elements and all the different permutations, right? I give you an abstract group, I need to give a representation. The representation is just permuting qubits. I have n qubits, and the symmetry group is, I'm just going to permute them. And I want my model to be invariant under qubit permutations. Why do I want to do this? Because problems with permutation symmetry are all over the place. Like if I want to learn over sets of elements or model relationship between pairs of elements in a graph or multiplets, or maybe I have problems defined on a grid, molecular systems, because the whole point is that all of those, for instance, you have a graph, right? A graph is just nodes and edges. Whenever you put it in a quantum computer, you're saying this node is qubit 1, this node is qubit 2, this node is qubit 3. This is an arbitrary choice. What happens if I said, okay, maybe the first qubit in my quantum computer is going to be this other node? Well, you can build a model that is going to be invariant under that relabeling of your nodes, right? This also works for studying multi-part entanglement or distributed quantum sensing. So how would an equivariant quantum neural network look like? Well, for instance, here's an example. You know, it's a very fancy name for this very simple circuit where I do the same rotation around x-axis to all the qubits by a parameter theta 1. You can see that this commutes with the action of the symmetry. If I interchange any pair of qubits, this layer is exactly the same. Then I can do a rotation around the y-axis, and then I can just couple all the qubits z to z, because that has to be permutation invariant, right? So if I repeat this circuit multiple layers, we've managed to prove that by embedding symmetries into your quantum neural network, you're going to have a bunch of really nice guarantees and properties of your quantum neural network. So in this special case, we've managed to find what I like to call the holy grail of properties. What does this mean? This does not have barren plateaus. For me, this is the first ever trainable deep quantum neural network. You can go as deep as you want. It's never going to have barren plateaus. We can prove that the variance is at most polynomially vanished. Then it's efficiently overparameterizable. That means that you can reach the overparameterization regime where most of the local minima are going to disappear. And you just need a polynomial number of layers. So you don't have to worry about local minima anymore. Then it's going to generalize really well from few training points. So by embedding symmetries, I don't have to give it that much data, and it's going to generalize really good, right? Because it doesn't have to learn the invariance into itself. Let me give you another example. Let's consider an equivariant, in this case, quantum convolutional neural network, where my symmetry group is going to be SU2. So this is an abstract group, and I need to think about what is the representation. So the representation of the group is I take a rotation. You can think about this as a 2 times 2 matrix, and I'm going to do the same rotation to all the qubits. This is like the example of classifying phases of matter. If I have 2 qubits and they're ferromagnetic, and I rotate them by the same unitary, this is still ferromagnetically ordered, right? And SU2 symmetries appear all the time in condensed matter. Like in certain spin chains, you can also relate them to entanglement measures, right? And we're going to be focusing on this architecture, which is the quantum convolutional neural network that was introduced by Aris Kong and their collaborators in this 2019 paper, where the whole idea is that you start with a quantum neural network that is acting on n qubits, and every time that you act, you're going to be trashing away qubits to reduce the feature space I mentioned, so that by the end, maybe I can just measure 1 qubit, and that qubit is going to have the solution to my problem. So the first thing that one needs to do here is find channels that are going to be equivariant. And now, because we're trashing, we're starting to include this new thing where the representation of my symmetry might change. For instance, if I have a unitary channel, I apply a unitary here, I apply a unitary here, it has to commute through. So the input representation and the output representation are the same. But whenever I trash away a qubit, my input representation is I rotate the 2 qubits with the same unitary, but in the output, I just rotate 1. So you can see here that representations of your group might actually change during a circuit. And you have to create gates that respect those representations, right? So in this paper, we were able to characterize the space of all 2 times 2 channels and all 2 times 1 channels. Oh, because this is something important that I forgot to mention, which is that in this paper right here, we show not just how to build equivariant unitaries, which we already know how to do with twirling, but also channels, because a channel allows you to take classical data and map it into quantum data, or have things where I'm trashing away qubits, right? So in this paper, we really try to go beyond unitary quantum neural networks to just general channels. Why do I care about the symmetry? Let's think about a problem of classifying phases of matter, right? And in this case, what's the model that I'm going to be working with is going to be the bond alternating XXZ quantum Heisenberg chain, whose Hamiltonian looks like a summation of this kind of terms where neighboring spins are interacting with X, X, Y, Y, and ZZ coupling, but the strength of that interaction is going to change from J to J prime to J to J prime to J to J prime, right? And what's really nice about this model is that the phase diagram is well studied, depending on this value data and the ratio between the 2 parameters, you're going to have different phrases like a trivial, topological, symmetry broken. And also the symmetries in this model are well characterized. We know that this model exhibits SU2 symmetry, right? So now we're trying to classify here. And what we're going to do is, for simplicity, let's just fix delta equals to 1, so that we're standing in a line here, and it's a model with 2 symmetries, right? So we're going to sample states from the trivial phase, states from the topological phase, and we're going to train a model to do this classification. And I'm going to give a model a really hard time. I'm going to give just 1 state from each phase, and it has to learn how to classify the whole phases, which is 1 state from each phase, right? So what happens if I take a quantum convolutional neural network where those 2 qubit gates are just like general gates, that one that has 3 nodes and 15 parameters, and the channels that map from 2 to 1 are also very general, right? In this case, what we're going to have is that the model, this is going to be its performance. I'm giving it 1 training point here with an X, another training point here with an X, And this is the classification diagram. This is like 0.6 classification accuracy. Might just as well throw a coin and try to do your classification. But what happens if now I create a model that is SU2 equivariant? Well, this is what's going to happen. I just give it two models, 2 points, and it can do a really good job at classification. This misclassification region, if I give it 2 more points or 1 more point in each phase, is going to completely disappear. And of course, if I have a hardware efficient ansatz and I give it a bunch of training points, eventually it's going to learn how to do this. But this is the minimal example where we show that with fewer data points, much fewer parameters, because the symmetry preserving model, I believe it only has like 4 or 8 parameters. I don't remember. It's very small. You can do training, and with very few training points, manage to generalize well. So what is the outlook of all of this? First, that geometric quantum machine learning provides a framework to create quantum machine learning models that have symmetries based on the problem that you're trying to solve. And we've already shown that it can help mitigate issues such as barren plateaus, poor local minima, or poor generalization. And for the young people of the audience, this is such a young field. Everything is an open question. There's so many low-hanging fruit in geometric quantum machine learning. And, I like plowing and picking the low-hanging fruits, and I know that people do too. So this is something that I encourage young people to get into, because everything is an open question. How does this work? What is the limitation? Where can we apply this? Everything is completely open. Of course, I'm going to make a disclaimer, which is that geometric quantum machine learning is not the end of the story. If you have problems with small symmetries, you can expect small improvements, right? So it's not just because you do this that you're going to be able to solve all of your problems. And finally, I just want to thank my collaborators, some of the students from our summer schools, some of our postdocs, my previous mentor, Patrick Coles. And I also want to take this opportunity to advertise that our group has open postdoc positions. You can apply at this link. And if you have questions, you can send me an email. Here's my email. And again, thank you very much for your attention, and to the organizers for inviting me.
Thank you so much, Marco. Thank you, Marco. And maybe we can share the link later in the Discord. Everybody, Marco's going to go to the Discord after this, after our questions here, so that you get to answer and ask even more questions there. And don't go yet, right? You've been very active in the chat, but hopefully you can still keep active, keep asking questions, because we're going to have a giveaway after our session of questions. So my first question for you, Marco, is related to the work that you have done in Guatemala. You have done a lot of work for promoting science, and I want to hear more about that.
So last year I was in touch with an amazing group of people in Guatemala that are trying, as you said, to promote science in Guatemala. Being from a developing country, there isn't really a lot of science being done at the country level, because whenever you have other issues that you need to solve, science is always not going to be a priority. But that doesn't mean that there's not people that are interested in science and that are extremely bright and want to try and do something in science. And sometimes people might have the opportunity to travel away and study abroad, but also a lot of people want to stay in their country and they want to do science there. So last year, researchers from Guatemala got in touch with me from the universities, and we organized via the ICTP Institute in Trieste a week-long course on quantum machine learning to try to get Guatemalan students and Central American students involved in this field and trying to get them excited with quantum machine learning. And it was a very nice experience. I felt very honored to have been invited to that. I also try to keep in touch with people back in Argentina, which is where I studied from my previous university and my previous work group, because, trying to give people opportunities that could be otherwise very hard to access is something that I take very close to my heart, because I was given the opportunity to, first study in Argentina and then come here to the US, and we just have to build a bridge for our communities. I think that trying to get science to people that might have, or to places where science might be underrepresented, it's always something that I try to do and take very seriously.
That's totally right. I agree. You have to do this extra effort to make sure everybody has access to the knowledge, to the technologies, etc. So at QHack, for instance, we're very proud of having this event being free and virtual, so that anybody, wherever you're in the world, you can enjoy this content from speakers, amazing speakers like you, Marco. And I also have maybe a motivation for people to participate in the hackathon, right? So, and somebody wanting to join Marco's group. You mentioned something about looking at people's achievements in QHack.
So yeah, this is very interesting because we hold every year at Los Alamos a summer school, and it's actually very competitive. We get I think last year like 400 entrants. So the people that are in charge of making the decisions and evaluating the CVs, of course, it's multiple people that do this because we try to keep it as less subjective as possible. You're giving a CV and you just have to get like a picture of a person's work through their CV and recommendation letters. So you can see their school, you can see their publications, but also for me particularly, I also look at hackathon participations. And we know, for instance, that the Xanadu's QHack hackathon is very non-trivial. You know, the problems are hard problems, they're very interesting problems, and you have to do like proper science to be able to get a good spot. So whenever I see a CV and it shows that you got a very high place in a hackathon, this shows working experience, right? And this might be very useful for some of the younger students that don't have a lot of papers. This is a way in which you can show in your CV that you have hands-on experience in the field. So for the younger students that might be doubting themselves, should I get into this hackathon? Maybe it's just going to be a lot of work. I would say give it a go. You never know. It might open some gates and some doors in the future, because for me, someone that gets a good position in hackathon absolutely has shown like proficiency in the field, just as much as a paper.
That's right. That's right. So here you heard it from Marco and from me. Now let's go to questions in the chat because there's a ton of them. A question from YQCat. I think usually we know what symmetries there are given the Hamiltonian, right? The symmetries we don't know about, maybe emergent gauge symmetries?
Yeah, that's a great question. I think that's coming sort of like in this example right here, which is how to identify symmetries in your data, right? So if you have data that is coming from a Hamiltonian, your Hamiltonian will inform those symmetries. So this is an absolutely valid way to find symmetries. If you think about other problems like the purity data set, right, there is no underlying Hamiltonian here. And we just identify symmetries by thinking about what are the properties that we're looking at and how those properties are going to get preserved. So this is one of those cases where I would say that how to find symmetries. If you have Hamiltonians, starting with the symmetries of your Hamiltonians, this is absolutely something that you can do. And even you might ask yourself, if I'm given a Hamiltonian, what are the symmetries of that Hamiltonian? There is some really nice papers out there, some recent work like Mark Wilde's group, where they take a Hamiltonian and they try to discover the symmetries in that Hamiltonian. So yeah, just the problem of identifying the symmetries on their own is really interesting. Again, low-hanging fruits all over the place, if you ask me.
Yeah, we love the low-hanging fruit. Helps us get started, get advancing. Now we have a question from Gizmo Sigma. Does this work for any group, or rather, what groups do you support?
Absolutely, fantastic question. I'm making an underlying assumption whenever I'm saying that. I'm just gonna go to the slide because I don't want to like talk in the air. Right. So when we said here, I am explicitly assuming that the action of my group is in this way. So that rotating my state is just applying a unitary or acting with the adjoint representation of this unitary in my state. So taking U rho, U dagger. So this is going to be true if your group is compact. So if you have a compact Lie group, you have a guarantee that will admit a unitary representation in your Hilbert space. If you don't have a compact group, how to build equivariant layers, open question. That would be something really nice to analyze. And some of those like more subtle questions, we talk about them in our tutorial. But what's interesting is that for quantum mechanics, almost naturally, all of the groups that you start with are going to be compactly grouped. So you don't have to worry too much because you already know that they admit a representation that is going to be unitary. But if you have classical data and your group might not be compact, that's different. But for discrete and compact Lie groups, we have theory.
Okay. Thank you. Thank you for that answer. We have more questions coming, and keep them coming because we have a giveaway. And because we want to ask Marco questions, right? So a question from Abby UBC. Is there a general technique for building symmetry preserving embeddings?
So in the paper that I mentioned, where we have the different tools, we present techniques to do this. And also in Johannes and the Jens Heiser group paper, they also have a way to do this. Now, depending on what your data is and what your symmetry looks like, you're going to have some freedom. For instance, we already saw that classical data has a given representation. Like it was like this changing x1 with x2, right? And whenever we go with quantum data, our representation was swapped, but it doesn't have to be swapped. It can be some other representation, right? So how to build those channels are going to depend on what your initial group and representation are, what your final representation are, and then you can build the in-between via the tools that we present in our paper. It might be more or less complicated. It's ultimately just linear algebra. So, you just put that in a computer, you solve a problem, and it's going to give you what the channels are. And as you can see, the representations are going to be coming into play because representations are not defined. In the classical data, they were defined. But whenever I go to a quantum computer, I can just choose whatever representation I can come up with, as long as it satisfies the group properties, right? So analyzing how the difficulty of creating an embedding changes as a respect of the output representation, the representation that I want acting on the Hilbert space. Again, I don't know. This is another great research question.
Yeah, a ton of great research questions, and more of them are coming.
And I'm sorry I'm not able to give answers. I'm just telling you that's a great research question.
That's a good answer. That's something you would want to hear. It maybe motivates the person asking the question to actually try it out, try to find the answer. We have one where maybe we'll be able to have a different answer. So the question from Sprig Litika is, does geometry in this situation mean that the models work particularly well on geometric data, or is just capturing the topology of the data?
Yes. This is general, right? So this should work for any type of data as long as your data has some symmetry associated to it. So if you have a learning task, you first identify what are the symmetries, and then you can implement this whole pipeline. But your data can be whatever it was initially, right? You just need to make sure that you can identify the symmetries and go from there. But there is no restrictions to what is the type of data that this is going to be useful for. It's not that you need to have special type of data to implement this pipeline. In principle, this is something, and geometric quantum machine learning is just one more tool for your quantum machine learning toolbox. So you have some data, you can ask yourself your questions. Are there symmetries that I can exploit? If there aren't, you do what you were previously doing. If there are, now you can add an extra step that is going to hopefully improve the performance of your model.
Okay, great. Let's go for another question, this time from Rihao Lee. Thanks for the amazing talk. I have a naive question. There are no naive questions, Rihao Lee. The question is, if the classical data has multiple symmetries with different representations, can the formalism handle such a scenario? Could you briefly touch on how to go about this?
Yeah, this is an amazing question. So what happens if I have multiple symmetries, right? Imagine that I give you a picture that lives in a square, and I can flip it this way, the image, or I can flip it this way. And those two symmetries are independent, right? So you can think about it as a Z2 doing this, flip and flipping back, get back to identity, and a Z2 flip here and flip here. So here your symmetry group would be given by the tensor product of those two symmetries. So you would say my symmetry is Z2 tensor Z2, and it has a representation given by those symmetries. So then now you can build the whole pipeline where your group is Z2 times Z2, and all the tools that we've prepared are going to be valid for this type of symmetries. Because that's the thing, composing symmetries is still a symmetry. You can think about it as a larger symmetry, and now you apply the tools to this larger composed symmetry. So yeah, this should work if you have multiple symmetries. And in fact, the more symmetries you have, probably the more of an improvement you can expect with these techniques.
That's good. That's the answer we want to hear. More symmetries is better, much better. Okay, thank you everyone for your questions. Keep asking them, and the ones that didn't get answered, you can ask them in the Discord. So Marco is then going to go to the Discord. But before you go, we're gonna have a giveaway. So Marco, we're gonna say goodbye to you, but everybody stay here for a minute for a giveaway.
Thank you very much. Take care, everyone.
Thank you so much, Marco.